So, further f of x bar is the maximum, local maximum, f of x bar is the local maximum if the partial f partial x1 square is negative or partial f partial x2 square is negative, right, and it is a local minimum if I have the second derivative of f with respect to x2 is positive or well x1 respectively x2 is positive. Okay. So, that concludes our second derivative test. Well, there is one final statement. Suppose the discriminant is 0, then our second derivative test fails. So, x is a degenerate, it is a degenerate vector, degenerate stationary point, right, or the nature, in this case the nature of this point x bar determined by higher order terms, right. So, determined by higher order terms, fine. Let us say cubic terms and so on, cubic or higher, right, because no longer we are able to determine the nature of the extremal just by looking at the quadratic term. So, we can continue our discussion for functions of several independent variable. I am just going to briefly state the result. So, for functions of 3 or more independent variables, for functions of 3 or more independent variables, I see that my stationary points are found by setting the gradients equal to 0, and the sign of f of x bar, the sign of this difference is going to be controlled by the quadratic term q of eta, but q of eta will have the form that I just am going to write. So, the sign of this difference is controlled by quadratic terms in the Taylor's expansion, given by q of eta equals eta transpose h of x bar eta, right. So, the quadratic terms are governed by this product. The sign of this vector product will tell us the nature of the extremal. Okay, where my h is the so called, so H is the so called Hessian matrix. Okay, and I am sure students are familiar with this matrix. This is of the form partial 2 partial f partial xi partial xj. So, this is my Hessian matrix, and so suppose H is definite. Well, all these concept of definiteness should be looked at in the standard multivariate texts, or the student should Google, because this is some basic concepts I am just revising. So, suppose H is definite. So, suppose my Hessian is definite, it is a definite matrix, then f has, the function f has a local extrema, right, extrema at x, and suppose H is indefinite. Suppose H is indefinite, then x turns out to be, x is a saddle point. X is a saddle point, and so further we can classify the first statement, namely if H is positive definite, then we expect that the local extrema is minima, and if it is negative definite, then the local extrema is the maxima, right. So, we can write down these further results. So, then I am going to end my discussion on this finite dimensional calculus by providing two results which are of extreme importance, especially when we discuss our optimization of functional calculus. The first result is in the form of the Morse lemma, which tells us how to distinguish between the saddle points, the local maxima and the local minima in the neighborhood of extrema. So, the Morse lemma, so this is my lemma 3 now. Lemma 2 was introduced in lecture 2. So, the Morse lemma says the following. It says that suppose I am given x naught, which is a non-degenerate stationary point, for a smooth function f, then there exists a smooth invertible coordinate transformation. There exists a smooth invertible coordinate transformation of x naught such that f of x minus f of x naught is, so there is a smooth invertible coordinate transformation of x naught coordinate transformation. Well, let me call this, well I have to say something about the coordinate transformation. So, there is a smooth invertible coordinate transformation from x j to x j of v, right, where my vector v, which is v1, v2, vn, is defined in a neighborhood of x naught. It is defined in the neighborhood of x naught of n of x naught such that we have that f of x is equal to f of x naught minus v1 square up to v lambda square plus v lambda plus 1 square plus and so on plus vn square, right. So, it essentially says that suppose x naught is a critical point, then I can find a certain coordinate transformation, a map in which when my independent variables are transformed, I can write down my function into this form that I have shown, right. So, this holds throughout n of x naught, right, where lambda is the saddle, it is a saddle, well lambda is the index, it is the index of, it is called the index of the point x naught, right. Now, so what is the significance of lambda? So, suppose, so notice this, notice what is being subtracted here. So, consider this quantity v1 square plus v2 square plus v lambda square minus v lambda plus 1 square minus so on until vn square, right. So, we call this as the Morse lambda saddle, right. Now, specifically if I have that, if my n is equal to, well lambda is equal to n, right, which means that all the terms are being subtracted v1 to vn, then what do I expect? I expect that my x naught is a local max, right, any function value at any point other than x naught near the neighborhood of in the neighborhood of x naught will be lower than the functional value at x naught. So, the conclusion here is, if my n, well, the index is n, then I see that my Morse saddle is a local extrema, a local maxima, right, and on the other hand, if lambda is 0, then my Morse saddle is a local minima, right, the functional value at x naught. So, the functional value at x naught is the lowest possible value among all such point x in the neighborhood of x naught in the second case. Okay. So, then I end my discussion by now stating a result in the form of a theorem. The theorem is known as the Sylvester theorem. Sylvester criteria, right. So, essentially it tells me that suppose I have so this criteria tells me about the condition for which a matrix, let us say the Hessian matrix, is when is it positive definite or when is it negative definite. Okay. So, conditions, so it is the condition under which the conditions under which the quadratic form is definite, right. So, for that let us consider, so the statement says let us consider the vector of the form x1 to xn, and let us denote an n by n matrix. So, let A denote an n by n symmetric matrix. So, the Sylvester criteria says, so with entries A I j. Okay. So, my Sylvester criteria says that a necessary as well as sufficient condition for the existence for the quadratic form to be positive definite is that all its principal minors is positive, namely in particular all the diagonal elements are positive as well as all the determinant of the matrix is positive. Okay. So, let me write down what I just said. So, for the quadratic form, the form is in this form x transpose A x. So, these are my bilinear forms that I have to check. So, for all the quadratic forms, this to be positive definite is that every principal minor of the determinant of the matrix A is positive, or in particular my determinant of A itself is positive, and all diagonal elements A j j, they are also positive. Okay. So, that is the Sylvester criteria for finding the positive or the negative definiteness of the matrix, and we now have the sufficient background to look at the optimization of functionals. So, let me now start with briefly start with the basic definition. So, the major description will come in our next lecture. So, second variation of functionals. Okay. So, I am going to look at the basic functional, the basic fixed point functionals. Okay. Well, functionals. Okay. So, we we are seeking smooth functions y from the interval x0 to x1 to R such that y of x0 is y0 and y of x1 is y1, and such that the extremal j of y, which is integral from x0 to x1 f dx, the functional has an extremum at y. Okay. So, then we assume we continue our discussion with the standard perturbation argument. So, assume a perturbation of the form y hat. So, this is a one variable setup. So, y hat is equal to y plus epsilon eta. We assume a perturbation of this form where epsilon is positive and eta is smooth, right. Epsilon is positive and eta is a smooth function, and then we use Taylor series. We use Taylor series in our on the integrand of f, right. We use Taylor series on the integrand of f. So, my f of x comma y hat prime will be f of x comma y prime. So, we are expanding about the extremal plus epsilon times eta of partial f partial y plus eta prime partial f partial y prime plus epsilon square by 2 eta square partial f partial y square and plus 2 eta prime partial to f partial y prime plus eta prime square partial to f partial y prime square, okay, plus order epsilon cube. Okay. So, then I can rewrite this from here. I can find what is the variation in the functional. So, my variation in the functional j of y hat, perturbed value minus j of y, is equal to epsilon of delta of j eta comma y plus epsilon square by 2 delta square of j of eta comma y plus order epsilon cube, right. So, our perturbation is of this form. Notice that we have only written up to second order. So, then where I know that this is my standard first variation, we have done a lot of problems on the first variation. So, we do not worry about it. Let us now look at the second variation. So, the second variation, so my second variation of this functional is of this form, integral of x0 to x1. So, notice the way how I write. So, eta square f y y plus 2 eta prime f y prime plus eta prime square f y prime times dx. Notice that this quantity is nothing but, this whole quantity is nothing but eta prime, this is nothing but, this is eta square prime, right. Now, so how does it help? Now, suppose using this information, suppose we do integration by we do integration by parts on this underlined quantity. So, we integrate by parts and we change this integral into this following form. So, eta square times f y y minus f y prime d dx of this quantity plus eta prime square of f y prime dx, right, this dx, and then we will show that the sign of this second variation completely depends on the sign of this quantity. Well, we will just state the result, but before that I just want to highlight, well, again even before that, let me also quickly introduce my sets H and S and H. So, S is the set from where I am going to pick all my extremal functions. So, it is all y from, so all y from C2 of x naught x 1 such that y of x naught is y naught, fixed point problem, y of x 1 is y 1, and my set H is the set of all perturbation functions such that eta of x naught is equal to eta of x 1 is equal to 0. Now, suppose, so I need to now connect the sign of the second variation with the location of the maxima or the minima. So, this next result, theorem 23, exactly does that. So, it tells me whether j del square j greater than 0 gives me maxima or minima and vice versa. So, it says the following, the result says suppose j has a local extremum, at y which belongs to the set S which we described above, then the first part of the result says that del square j is positive, implies that y is a local minimum. This is for all eta in H, and if the second part says that if del square j is negative, then I get that y is my local maximum, right. So, that is the relation between max and min and the sign of the second variation. Okay. So, similarly we can see that, so condition A and B are related to the semi definiteness of the Hessian matrix. So, when we eventually calculate the second derivative, the second variation, we have to look at the definiteness or the semi definiteness of my Hessian matrix which is involved in this setup. Okay. So, then I am going to finally end this topic here by stating one of the very vital results known as the Legendre condition. So, the Legendre condition is as follows. So, this is the first of the results that I am going to state in order to determine the sign of the second variation. So, the idea is to determine the sign of del square j, right, because once we know the sign, we can immediately say whether the extremum involved is maxima or minima. So, the Legendre condition exactly does that. So, the Legendre condition, so it says the following, it says that it is in the form of a result theorem. So, it says that let us assume that j is my functional. So, it is the functional which is the basic fixed point functional. So, basic fixed point functional that we have began with, and where my integrand f is a smooth function. When I say smooth, this is continuously differentiable up to second order function of x, y and y prime. Suppose j has a local minimum in S at y, then the result says that f of y prime must be non-negative for all x in the interval under consideration. So, this is the crucial quantity whose sign needs to be checked to determine whether we have found a local minimum or not. Again, the proof is not going to be shown here, but for the proof I am going to refer to this particular expression for the second variation of j, saying that almost the entire the most dominant term in this expression is the second term, and hence the sign is completely determined by the second term. And for the complete proof, I am going to refer to this following text, Calculus of Variation by Bruce Van Brunt, that we are also following in this course. This is the book published by Springer. So, students are asked to refer for the complete proof. Let us quickly look at an example of the application of Legendre condition. So, so let me consider a functional of the form j of y is equal to integral minus 1 to 1 x times square root of 1 plus y prime square dx. We see that f of y prime is given by the following: x by 1 plus y prime square to the power 3 by 2. Now, this changes sign in the interval, right. So, this changes sign from x minus 1 to 1, right. The denominator is always positive, but the numerator changes sign, and students are asked to check that the solution to the Euler-Lagrange equation for this functional is not a minimum, right. Students are asked to check, and this Legendre condition guarantees because the sign changes, right. We will end this discussion by giving one more example as of that of the catenary, right. So, recall in our catenary problem, we will look at the unconstrained problem. Okay. So, in the catenary problem, my f of x comma y prime is of the form y minus lambda, the integrand y minus lambda times 1 plus y prime square, and let me quickly evaluate this Legendre derivative f y prime. This comes out to be y minus lambda divided by 1 plus y prime square to the power 3 by 2, right. Notice that the sign of y minus lambda determines the sign of f y prime, and if people recall that y minus lambda, y being the extremal, they recall that the solution in this case was 2 zeta hat cos hyperbolic zeta hat 2 x minus 1. This problem was done few lectures back, and notice that the sign of y minus, so this is my extremal solution coming from my Euler-Lagrange equation, and the sign of y minus lambda is, well, cos is always, the cos hyperbolic is always non-negative. So, the sign is completely determined by the sign of xi hat. So, students are asked to check that positive solution, the positive root gives us the minima, and that is confirmed by the Legendre condition. So, thank you very much for listening, and in the next lecture I am going to look at, well, we will begin with a slightly bad news that Legendre condition is not going to be sufficient in determining whether a extrema is maxima or minima. Well, it helps, but it is not the condition that we are after. So, thank you very much for listening. Thanks a lot.